Hey guys, so we'll just do a quick lesson to start off this new unit here. This one, we're going to be doing a lot of graphing. So we've worked with exponential and logarithmic functions before. Now we're just going to look at transformations of them. So it'll be an easy start to the unit. So what I need to remind you about is what can exponential functions look like? And then once we remember what they can look like, then we can do the transformations to them. So let me just switch over to Desmos to show you some general shapes that they might look like. So if the base of the exponential function, and I should mention what makes it an exponential function is that the x, the variable, is in the exponent. So what are the general shapes of what they could look like? Well, if the base of the function is a number greater than 1, so let's say 2, the function looks like this. It's an exponential growth function. If the base is between 0 and 1, so like a half, it's an exponential decay function, so it would look like that blue function. And then either of those could be flipped upside down with a vertical reflection. So when we do transformations of exponential functions, it's going to look like one of those four general shapes, but we could transform it, stretch it, compress it, or shift it left, right, up, or down. So let me get rid of those ones, and let me just remind you about what a, k, d, and c do to transform a function. So this is the 2 to the x function. And also notice there's a horizontal asymptote at y equals 0. So this exponential function, the a value can vertically stretch it and compress it. So as I adjust the a value, notice it's getting vertically stretched or compressed. So let me put a back to 1. The k value does horizontal stretches and compressions. And the d and the c value are going to do the shifting left, right, up, and down. The d value would shift it left and right, and the c value shifts it up and down. So notice the only parameter that is going to change where the horizontal asymptote is the c value. When c is at 0, the horizontal asymptote is at y equals 0. But if I make c equal to, let's say, 1, the horizontal asymptote, let me just draw it in, would be at y equals 1. So the c value tells you where the horizontal asymptote is moved to. So in the first part of your lesson, it's just showing you those four general shapes and then talking about the properties of those exponential functions. So an important property that we just talked about is that the horizontal asymptote can be shifted by the c value. So you might want to make a note, the horizontal asymptote is at y equals whatever the c value is. So whatever vertical shift has happened, that tells you where the horizontal asymptote is moved to. When we're graphing these transformed functions, we're always going to graph the horizontal asymptote, the y-intercept, and at least one other point. We'll do two other points. And the y-intercept occurs when x is 0. So what we're going to do in our table when we do a transformation of an exponential function, we're going to choose an x value of 0, and then also negative 1 and 1. And that'll give us a good shape of the graph. So let's do an example. It asks us to sketch the graph of this function and this function. Those are both transformed 3 to the x functions. The base of the power in both of those is 3. So notice since the base of the power is both 3, these are transformed 3 to the x functions. So when we graph them, it'll be useful if we have a table of points from the parent function, from the 3 to the x function. And we're always going to choose the same x values. Negative 1, 0, and 1. And then we can calculate the y values by plugging those x values into this equation that tells us what y is equal to. So when we do 3 to the power of negative 1, that's 1 over 3, which is about 0.33. When we do 3 to the power of 0, anything to the power of 0 is 1, and 3 to the power of 1 is 3. Notice I have a fourth row here. These 3 points will be enough to get a good general shape of the function. This fourth row, I add this so that we can comment on what the horizontal asymptote is. So the horizontal asymptote of any exponential function that hasn't been shifted is at y equals 0. Now let's use these key points to come up with transformed points for these two transformed functions. So let's start with this one. So I'm going to label which parameter is which. So this 2 is an a value, this 4, well, actually the d value is negative 4. It's always the opposite sign of what you see. And the c value is negative 5. I'm picking those parameters out because I know the transformed exponential function always takes this form. A is in front of the base of the power, k and d are in the exponent, and c is added after the power. So if we know that general template, it makes it easy for us to pick out those parameters here. And now we can apply those transformations. So the only horizontal transformation that is happening, since d is negative 4, would be moving left 4. And I can do that by subtracting 4 from all the x's. The y-coordinate, there's a vertical stretch by 2, and it shifts down 5. Vertical stretch by 2 from the a value, and shift down 5 from the c value. So if I double all the y's and subtract 5, I do those transformations. So now what we'll do is we'll take these points, plug them into this equation, and we'll take these points, plug them into this equation, and we get the table of values for the transformed function. So let's do the x values first. So negative 1 minus 4 is negative 5. 0 minus 4 is negative 4. And 1 minus 4 is negative 3. To do the y values, we're going to need to double 0.33, so about 0.67 will get us to 2/3. Minus 5, that's negative 4.33. 2 times 1 minus 5 is negative 3. And 2 times 3 minus 5, that's 6 minus 5, that's 1. So there's our table of transformed points, and then we also need to comment on where has the horizontal asymptote moved to. So the horizontal asymptote is always at whatever the c value is. So our c value is negative 5. So our horizontal asymptote is at negative 5. So now what we can do is we can take all of these points, plot them, and see what the transformed function looks like. So let me just split my screen here, and we'll graph it. So let's graph that transformed function. So I'm always going to start by drawing the horizontal asymptote. So the horizontal asymptote is at y equals negative 5. So I'll do that first. So here's the horizontal asymptote for it. So the function will never cross that horizontal asymptote. It'll approach it as x goes to negative infinity. And let's plot our 3 points. Negative 5, negative 4.33. So negative 5, negative 4.33, that's about right here. Negative 4, negative 3, that's about here. And negative 3, 1, that's about here. So this function looks like, let me try that again, see if I can connect them a bit better. Here's what the function looks like. This is our f at x function. So there's our first transformed exponential function. Notice it's been vertically stretched, it's been shifted left 4 and down 5. Alright, let's try the other one. Let me put it back to single page view for us. And let's do the next function. So for this one, make sure, it might be helpful if you see me put brackets around that base of the power 3 so that you can see that the a value is actually negative 1. And we have a k value of 1/2 and a c value of 4. So when I do the transformations, let's do x first. So a k value of 1/2, remember that the k value, the transformation it does, is always by its reciprocal. So it's actually going to do a horizontal stretch by a factor of 1/1/2. So a horizontal stretch by a factor of 2. So I would have to double all the x's. And then I need to do a vertical reflection, so multiply the y's by negative 1, and shift it up 4. If you want, I can write a reminder of how we come up with these transformations. Whatever goes here is always ay plus c. And whatever goes here, we always take our x value and divide it by k, and then we add the d value to it. And remember, the d value is always the opposite of what you see. So for this one, we did x plus negative 4, which is x minus 4. Here we do x over 1/2, which is 2x. Okay, back to these points. Okay, so I need to do 2 times negative 1. So keep in mind, I'm doing transformations to these points. So plug in each of the x values. 2 times negative 1 is negative 2. 2 times 0 is 0. And 2 times 1 is 2. Now let's do the y values. So take each of these y values and plug them in here. So negative 0.33 plus 4 is 3.67 approximately. Negative 1 plus 4 is 3. And negative 3 plus 4 is 1. And lastly, our horizontal asymptote would be at y equals whatever the c value is. So at y equals 4. So now that we have those points, we can just plot them on our graph, and we have our second transformed function. So I'll go back to split view. And we'll graph the blue function, the g at x function. So it needs a horizontal asymptote at 4. So it's going to look a little confusing having 2 functions on the same grid that both have a horizontal asymptote, but I've got it color-coded here, so it should be alright to figure it out. So y equals 4 is our horizontal asymptote. And then we can plot our 3 points. So negative 2, 3.67. That's right about here. 0, 3. And 2, 1. So this function looks something like this. Let me try and do that a bit better again. It looks something like that. So there we go. We've got both of our exponential functions. I should label this one. This is our g at x function. Just remember, whenever you're graphing the exponential functions, make sure you know they have a horizontal asymptote. Make sure you put arrows on both sides to show they are continuous functions. And make sure you don't cross its own horizontal asymptote. Okay, so I think that's about it for exponential functions. If there's any questions with either of those, make sure just let me know in the chat. I think you guys did transformations of exponential functions in your previous course, so this should be pretty familiar to you. But we needed to start with this because the graphs of these are very connected to the graphs of log functions, and that's what we're going to do next. Alright, we'll move on to log functions. So what makes something a logarithmic function is if the variable is in the argument of a logarithm. Now, a logarithmic function is the inverse of an exponential function. So instead of having horizontal asymptotes, they're going to have vertical asymptotes. Let me just show you what the 4 general shapes of logarithmic functions could look like. So if a logarithmic function has a base that is bigger than 1, so for example 2, it looks like this red function here that has a vertical asymptote at x equals 0, and it's increasing over its domain. If the base is between 0 and 1, it's going to be decreasing over its domain, but still has that same vertical asymptote. And then these functions could be horizontally reflected to look like either of these. So these are the 4 general shapes you will see for a logarithmic function. And then what we're going to do to those shapes is we're going to transform them using a, k, d, and c again. So here's that log base 2 of x function. Same thing, we're going to be doing vertical stretches and compressions by manipulating the a value. Horizontal stretches and compressions by manipulating the k value. Let me just put these both back to 1 now. And then also shifting left, right, up, and down. So shifting up and down is not going to change where the asymptote is. But if we shift it left and right, that will change where the asymptote is. Notice if I make the d value 4, the vertical asymptote is now at x equals 4. So the d value tells us where the asymptote is for a logarithmic function. So let's make a note of that. So when we're graphing a logarithmic function, it doesn't have a horizontal asymptote, it has a vertical asymptote that is shifted by the value of d. So our vertical asymptote is always at x equals whatever the d value is. And then to get a good shape of the graph, we're going to get 3 other points. We're going to get the x-intercept, and we can find that by setting y to 0. and then at least one other point, we're going to get two other points. And with logarithmic functions, we actually don't choose x values. We actually choose y values. We choose values for y and then calculate x. Let me show you why. Let's look at these two logarithmic functions, f at x and g at x. So those are both transformed log base 3 of x functions. Notice they both have the same base. So their parent function is this function right here, y equals log base 3 of x. Now we talked about that function would have a vertical asymptote at x equals 0, but now we need 3 other points. It's actually easier for us to choose y values and then calculate x. Let me explain why. Let's rewrite this in exponential form. If you remember your properties of logarithms, that function, what this function actually tells us, the y value tells us the exponent that goes on 3 to get the argument x. So if I rewrite this in exponential form, it would be x equals 3 to the power of y. That's what this equation means. What I wrote above it is equivalent to it. Y is the exponent that goes on the base to get the argument. So 3 to the y equals x. So you can see now, x being isolated, it would be easy to calculate that if we just subbed in values for y. And the values we're going to choose for y are -1, 0, and 1. So when doing logarithmic functions, choose values for y, sub them into this exponential equation we made that's equivalent to the logarithmic equation, and calculate x. So if I plug this -1 in for that y, 3 to the -1 is a third, so it would be 0.33. Plug 0 in for this y, 3 to the 0 is 1, so that tells us x would be 1. And 3 to the 1 is 3, so x would be 3. So logarithmic functions, choose values for y, calculate x. And now the rest of the question is the same. Just do our a, k, d, and c transformations to the points of that parent function. So this function has an a value of -4, a k value of 1 and no d value, and a c value of 2. If there was a k and a d value, we would see them in brackets with the argument, because here's the general template of a transformed logarithmic function. A is in front of the log, and c is added after it. K and d are part of the argument. So back to this function, we only have to worry about a and c. There's no transformations happening inside the brackets with the argument. So the x values are staying exactly the same. But the y values, vertical stretch by 4 and a vertical reflection, I do that by multiplying it by -4, and then up 2. So let's do those transformations. So like I said, all the x's are staying the same, so I just keep those x values. But then the y values, I have to plug them all in for that y. -4 times -1 is 4, plus 2 is 6. Plug 0 in, I get 2. And plug 1 in, I get -2. And the vertical asymptote is always at x equals whatever the d value is. And the d value is 0 for this. It hasn't been shifted left or right at all, so the vertical asymptote is still at x equals 0. So let's graph that function. Let me go back to split screen. And let's plot all the points. And I'll start by drawing the vertical asymptote at x equals 0. So vertical asymptote right on top of the y-axis. And then we'll plot our points. So 0.336. That's about right here. 1, 2. That's about here. And 3, -2. 3, -2. It's about here. So this function looks something like this. And this is our f at x function, so I'll label it. So let me just make this bigger so you can compare your graph to it. Make sure on your function you've labeled it, you've got arrows on both sides, and you're never crossing the vertical asymptote. Okay, we'll do one more graph. We'll do the graph of g at x. So this one, we need to do a horizontal reflection, shift left 2, and down 4. So the a value is 1 this time, so I don't have to worry about that. And the c value is negative 4, so down 4. So to y, I would just have to subtract 4. But to x, I have to do a horizontal reflection, so I would have to divide it or multiply it by negative 1. And then I need to shift it left 2, because the d value is actually negative 2, and I can do that by subtracting 2. So let's do these transformations to those points, the points of its parent function. So let's plug them in. Plug in 0.33 for x, and we get negative 2.33. Plug in 1 for x, we get negative 3. Plug in 3 for x, we get negative 5. And then we'll do the y values, plug them into this equation we made here, y minus 4. So we get negative 5, negative 4, negative 3. And the vertical asymptote is equal to x equals whatever the d value is. And in this case, the d value is negative 2. So x equals negative 2. Remember, the d value is always the opposite sign of what you see. So let's graph these points. Start by doing your vertical asymptote at x equals negative 2. And then we'll plot all 3 of our points. So here's x equals negative 2. And then we'll plot our points. Negative 2.33, negative 5. That's about right here. Negative 3, negative 4. And negative 5, negative 3. So the function would look something like this. Arrows on both sides. Label it with its function name. And there we go. Let me zoom in on this so you can see it. There are 2 transformed logarithmic functions. So I think that's all I have for you guys today. Yep, that's it. So I just wanted to show you how to graph transformed exponential and logarithmic functions. The main thing that is new for you in this lesson is making sure that when you are getting the points for a logarithmic function, that you are choosing the y values and calculating the x values. That's the main difference. That's the main thing people forget. Because if you try and choose x values and then calculate y, it's not easy if you don't choose great x values. Much easier if you choose y and calculate x. And then you ensure that you get a good shape of its graph as well. Alright, so if there are any last questions, feel free to put them in the chat. And if not, just make sure you guys all have a great weekend, and I'll see you guys all next week. Alright, I will end the stream for you guys. See everyone later.